Ah, welcome. Today I made a video that's going to go over some of the basics of projectile motion and go over some of the sample physics classroom problems that were assigned to you. Hopefully, when you look at a picture like this, it's starting to make a little bit more sense. You understand that projectile motion is two-dimensional motion. And because it's two-dimensional motion, it's going to be moving on both the x and the y axis. And together, both of those axes will describe the motion of the object that moves two-dimensionally. So we have component parts of v naught x, v naught y, of horizontal quantities and vertical quantities coming together to make final quantities. And that's what we're going to get into now. So, in projectile motion, the horizontal and vertical vectors are independent one another. What does that mean? Well, let's take a look at the charts that we've been looking at so far. We have here a drawing of projectile motion where we have a horizontal velocity of 12 and a vertical velocity of 20 meters per second, respectively. Now, I went over how to fill in these diagrams. Each dot indicates being in the air for 1 second, and I said that the horizontal arrows never change. So if you start off with 12, every dot gets a horizontal arrow of 12. And we're going to go over why they don't change in just a sec. But I said every dot gets a horizontal arrow of 12. So we're going to put these horizontal arrows at every single dot and label them 12 meters per second because the horizontal arrows don't change. Awesome. But the vertical arrows do change. Now, why would the vertical arrows change when the horizontal arrows don't? Well, projectile motion is moving in two dimensions. Once in the air, the only thing pulling on it is gravity. Nothing's pulling it right, nothing's pulling it left. So it will have no acceleration on the horizontal axis. If you remember, acceleration is defined as the change in velocity over time. So when we say there's no acceleration, what we mean is there's no change in velocity. If there's no change in velocity, the velocity stays the same. However, on the vertical vectors, we do have an acceleration. Our acceleration is gravity. Now, I know I said that gravity is negative 9.8 meters per second squared, but for simplicity, let's go ahead and call gravity negative 10. Let's round it to the nearest whole number, just for simplicity. And remember, acceleration is how much the velocity changes. So 20 plus negative 10 is 10. Now remember, do not put the signs next to your numbers and vectors. No positives, no negatives. Because the arrow indicates the direction. The arrow indicates the direction, so you do not need to put positive 10 or positive 20 when you're labeling your diagram. When you're putting numbers in the chart over here, you will need to put signs because there's no arrows to indicate the direction. So let's go back to labeling this diagram. Vertically, it's thrown up 20, 10, 0. You don't need to necessarily label this 0, but I like to just illustrate the point that at the top of the path, there is no vertical velocity. That doesn't mean the ball isn't moving. It just means it's not moving vertically. So 20, 10, 0, negative 10. Wait, you don't draw the negative. You draw the direction. So I'm going to put down 10 meters per second. Down 20 meters per second. And I know that means negative. So this is how we label our drawing. We understand that horizontally there is no acceleration, and vertically there is an acceleration. One more thing to note about these diagrams, the numbers that you start with, the 12 and the 20, are the numbers that you should end with. The speed it leaves is the speed it returns, but opposite direction. So if you start with 12 and 20, you should have 12 and 20 as your final arrows. 10 and 12, 10 and 12. There's a symmetry here I want you all to see. Okay? Until you get to the very top. That's like the very peak. Okay, so let's go back to this chart. Let's go back to this chart here. What is the V0x? Well, the V0x is the initial horizontal velocity. That's 12 meters per second. What is the V0y? Well, that was 20 up, or positive 20. These numbers right here are the initial x and the initial y. Initial y, initial x. V0y, V0x right here. They're the initial velocities the ball is going. Now we could go ahead, we solved for velocities at a bunch of different points in time. And that brings me to the next thing. All of these variables cannot move through the columns. So if I have a V0y, if I'm talking about y quantities, I have to stay on the y side. If I'm talking about vertical quantities, they have to be here. If I'm talking about horizontal quantities, they have to be here. But time is a scalar quantity. Time doesn't have a direction. So time can transcend the columns. What do you mean by that? So you can make a chart for every second in time. So these are two charts that what we can have is this. I want to be very clear. We could say that the V0x was 12, positive 12 to the right, and we can say that the V0y was positive 20. We're referencing the picture that we were just looking at. And the AX will always be 0 in projectile motion, and the AY will always be negative 10, really negative 9.8, but negative 10 meters per second squared. These will always be true. These are going to be constants for every time we deal with a situation. Once you know the V0x, the V0y, they never change. They are constant once you know them. Every problem might have a different set of them, but they are constant. But every problem, every projectile motion problem will have an AX of 0 meters per second squared and an AY of negative 10 meters per second squared. So what I'm trying to show you is this, that if I say time is 1 second and time transcends the column, so if this is 1 second, this is 1 second. If I use this 1 second with these values, what I'm finding is the velocity at 1 second, the horizontal displacement at 1 second. What I'm finding here is the vertical velocity at 1 second, the vertical displacement at 1 second. And then I can make another chart for 2 seconds. And I could just keep doing this for every second in the air. Every second, every moment in time can get its own chart. Because if you think about it, as the ball moves through the air, its horizontal and vertical displacement are changing. So every second in the air will have a different value of dx and dy. The vertical speed is changing at every second. So every second will have a different vy. So you will be making this chart a lot. It will be helpful. Just know that for any projectile motion problem, these never change. These never change. But once you know, for whatever problem that you're working on, the initial x and the initial y velocity within that problem, these values never change. Within this problem, these values never change. So, okay, same diagram. Let's go. I told you that every second has a unique Vx, Vy, all that stuff. Okay? I absolutely told you that. In fact, we already labeled this diagram. In fact, let's do it again super quick. 20, 10, 0, 10 down, 20 down. Horizontally, it's 12, 12, 12, 12, whoops, and 12. Okay? You knew that already. So, okay, how am I going to fill in this chart? Well, I told you that each dot represents a second. When you, in projectile motion, in physics in general, when you start off, that's 0 seconds. That's like when you start the stopwatch, how fast it's going when you start the stopwatch. So when it's in the air for 1 second, that means it's already been moving for 1 second. 2 seconds, 3 seconds, 4 seconds. Well, you correctly told me that the horizontal velocity never changes. So the Vx is going to be 12 every single time. I don't need to make a full chart for all those seconds. I can just follow this pattern. I can just follow this pattern. The Vy's, well, now we got to go ahead. They're still here. At 0 seconds, the Vy was 20. And then at 1 second, it was positive 10. Okay, so I'm just looking at the diagram that I've already made, and I'm showing you where these numbers come from. Remember, negative means down. Because that 10 is next to a down arrow, it's going to be negative. Okay, so here's the thing that's a bit tricky. When I'm asking for speed, I'm asking for total speed. So I'm asking for the sum of the two vectors, the resultant vector. Or another way of thinking about it is the hypotenuse of the triangle that these two vectors make. Because speed incorporates both directions. When I'm just saying how fast, if I took a radar gun and was taking the speed of a ball in the air, it's not going to tell me, oh, well, this ball is moving horizontally 12 meters per second and vertically 20 meters per second. It's not going to do that. It's just going to give me a final speed. What is the speed that would be read on the radar gun? Well, the speed of the object is the combination of both horizontal and vertical speeds at any given point in time. So to get the hypotenuse of a triangle, you have to use the Pythagorean theorem, which is a squared plus b squared equals c squared. Another way of thinking about this equation is vx squared plus vy squared equals v squared. So we are going to use the Pythagorean theorem a lot. We are going to combine the horizontal and vertical vectors to get the speed at any point in time. I'm not going to work out the work for each individual problem, but what I am going to do is write the answers here. .32 meters per second. What I did was 12 squared plus 20 squared equals c squared, and solve for c. That's the speed here. That's how fast the ball was thrown. because at 4 seconds you have the same numbers. Wait a minute, they're not the same numbers. This is positive and this is negative. I know, but when you square a number, it always becomes positive. You need to be smarter than your calculator. Some calculators, when you square a number, gives you a negative answer. Be mindful of that. What it's technically doing is order of operations. It's doing the exponent before it's doing the negative. So you need to put all your numbers in parentheses to prevent that. Your parentheses proficiency must be profound. So at 0 and 4 seconds, you're going to have the same speed because you have the same numbers. Go ahead, try it out. See if you can get these numbers. At 1 and 3 seconds, you both have the numbers 12 and 10. So when you do a squared, b squared, c squared with that, you're going to get 15.62 meters per second. And at 2 seconds, I know your gut feeling. You're like, oh, at 2 seconds it's going 0 at the top of the path. It's going 0 vertically, but it still has a horizontal speed. So the speed at the top of the path should be 12. So I assigned you a physics classroom. And on this physics classroom, there are a lot of really neat questions. Well, neat from my perspective. So on this first set of questions about horizontally launched projectiles, you have to go ahead and select the diagram. And I don't know which one it is. I'm not going to tell you. But you got to pick the diagram, one of these 7 diagrams that best represents how a projectile's path of travel, the parabola, and the velocity vector should be at each point in time. Select the diagram that works, and then hit this, select this diagram. This part should not be too bad. Now, this part we just did. But let's look at it in terms of this problem. A projectile is launched horizontally from a cliff at 12 meters per second. Well, that to me means that this arrow is 12. That's what that's saying to me. And because it was launched horizontally, I could assume that the y vector starts off at 0. Oh, in fact, they gave that to me right here. So, okay, it wants me to fill in the Vx and Vy every second in the air. I know the Vx never changes, so this is going to be 12s down the whole way. And I said in the charts, you had better include your negative signs because Vy has it says for G, it even says it right here, use -10. -10 at B. See? -10. -20. Well, you don't put the negatives in the arrows. I understand that. I know. So what I said was you never put the negatives in the arrows, but I'm just illustrating a point. But you're right. Thank you. If you did this on a quiz, I would mark you so wrong for putting the negatives next to the arrows. But you better have the negatives in the chart. Okay, I'm going to erase those negatives. But fundamentally, we know how to label this diagram. That's what it's asking you to do. You got this. So, I said at any moment in time, you could calculate the horizontal displacement and the horizontal velocity. Let's assume that the V0 x's and V0 y's never change. So let's go back. We can even go back. We can go back to our old problem. Oh, that should have been This should have been 20. 0. This should have been 0. The previous page had a 0 V0. I apologize. I wrote the wrong number there. That should have been a 0. Excuse me. So the V0x is 12, and the V0y is 0. And I'm asking you to fill out a chart where you're going to solve for a bunch of displacements. And I say the V0x, the V0y never change. And I know that the AX is always going to be 0, and the AY is always going to be negative 10. So how do you solve this? What you do is use the kinematic equation D equals V0 T plus 1/2 AT squared. You use this equation for every single spot. Okay, I don't know how to do that. Well, let me show you. Well, I think we could assume that you always start off with 0 displacement at 0 seconds because you haven't gone anywhere yet. And if you really want to go ahead and sub in 0 seconds into this equation, feel free. But let's go ahead and solve for dx at 1 second. So this is always going to be the equation you use, but you're either going to plug in x values or y values. So for dx, okay, I'm using x values. So I got to use V0x, which is 12, right? I'm going to use the time of 1 because I'm solving for the dx at 1 second. Plus 1/2. AX is 0. Oh, and the time is 1 again. Because AX is 0, this whole part of the equation will always fall out. 0 times anything is 0. dx equals 12 at 1 second. And then I'm going to plug in 2 seconds, and I'm going to get 24. I'm going to then plug in 3 seconds and get 36. And I'm going to plug in 4 seconds and get 48. Awesome. Okay, that's x. What about y? How would a dy equation work? Well, we're going to use y quantities. We are going to use y quantities. So the V0y is 0. I apologize. I did write the wrong number. So this is 0 times 1. Wait, didn't we already do 1 second? We did 1 second for dx. We did not do 1 second for dy. But remember, 0 times anything goes away. 1/2 negative 10. I thought you said that this whole part is 0 and goes away. Again, now that we're using y values, we have to use all y values. That part of the equation only cancels away in the dx. So dy equals, this is gone. 1/2 of negative 10 is negative 5. 1 squared is 1. dy is negative 5. And then you're just going to plug it in again and again with all the y values. Again, the V0y never changes. The V0y never changes. So watch this. All I'm going to do is erase, erase, erase. All I'm doing is this. Watch this. I'll make it a different color. 2 times 0 is 0. 2 squared is 4. Negative 20. What? What about 3 seconds? Erase, erase, erase. There is going to be a pattern here, gentlefolk. 3, 9. What? Are you saying erase, 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 that there's patterns to all of this? Well, of course I am. It's physics. Why is it negative? Because it's like, let's think about this conceptually here, right? If you have a V0, it's like the picture we just saw. If you have a V0y of 0, like a little toy car going off a table, it's going to be going down. It's going to have a negative displacement. So what we're saying here is that, like, at 1 second, we have a dy is down 5, and then a dx is 12. That's what we're saying. And then at 2 seconds, you're going to have another dy and another dx, and so on and so forth. So when the question on the physics classroom is talking about x position and y position, what it's really talking about is distance or displacement from the starting position. So even though it says position, you can treat it like distance. So we actually just solved this chart already on the previous slide fully. Think about it. dy at 1 second, dx at 1 second. dy at 2 seconds, dx at 2 seconds. And so on and so forth. So you can conceptually understand what you're solving for. Nice. Now, the next set of problems on angle-launched problems might actually be even a little bit easier now that we've done all that practice. So essentially what it's saying is rank the following spots based on greatest to least horizontal or vertical speed. Now I'm going to give you a hint. In projectile motion, you know that the vertical speed is always going to, the horizontal speed. The horizontal speed is always going to be the same. Same. And how did I get it? Look at this. You got to look. If you're just listening to me, you have to look at the screen. That's what you got to do. But how am I going to know which Vy is the greatest? Concept. You understand that as the ball goes up, it slows down. And as it comes back down, then it speeds up. So I have a choice between B, E, and G. We don't care about direction. We just care about absolute speed. The lower to the ground, the faster it's going. This is going to be the fastest. Then G, then E. And you know that because if I put in the numbers here, you would know that B would have a bigger number than G based on its position. Here, now it's going to ask you to select things that are true, but be sure to read the questions carefully. It's not asking about the whole time. It's going to give you a specific set of locations to consider. I mean, you know about the horizontal speed already. I don't need to tell you. But you are going to need to think about vertical speed. And when it's talking about speed, it's not talking about direction. Speed does not have direction. So from E to I, you know that'd be increasing. 0, 10, 20, 30, 40. In fact, I can even count exactly. I know that this is going to be 40. I know that's down 40 because this was 0, right? 10, right? Look at all the things I know here. Look at all this. You didn't know you knew this. You did. And then if this ends up going down 40, this is going to be going up 40. What? Wow. I didn't realize I could know all this. But you can. Nice. This one is having you drag and drop the appropriate vectors at each spot. There's no numbers here. You could figure out the numbers if you wanted to, but there are no numbers here. And it gives you, what it's going to do is, as you can see, it gives you this one little spot. So, right? So you know, right? You know that your arrows have to be relative to that. So we know that the blue arrow is going to be the same because the horizontal doesn't change. If you don't know that now, well, so we know from the get-go, those are not the answers. because they do not have the same horizontal length as what's highlighted on the screen. Drag and drop where these fit. Will the C red arrow be bigger or smaller than the B red arrow? Well, because it's going up, it's slowing down. You know it's got to be smaller. And at the top of the path, there's no vertical arrow, but that horizontal arrow remains constant. Now, this is everybody's favorite. Everybody's favorite. We did this before, and we're doing it again. Remember when I had those things like a rock with a speedometer? But this is what you do. It's all about those charts. Make those charts. Make those charts. It's going to give you some information. Bam. Here's the starting information. It says here the Vx is 20. I didn't even read the problem yet. I should probably read it. And the Vy is negative 10. It says a ball is launched upward at an angle. The diagram at the right shows the approximate values of the horizontal and vertical velocity vectors. Bam, right here. Match the 3 timers. So 1, 2. Your goal is to drag these timers to the appropriate vectors. Now, how are you supposed to know which time goes to which vector? Well, let's go back and look at our chart. We know how to fill this chart in. We know that the Vx is never changing, so we're going to have 20s all around. So let's go look at our possible answers. We know that the x has always got to be 20. Deleted, cannot be that. Deleted, cannot be that, because the x was not 20. Okay, we have 4 possible answers just based off the x's. Now I know, remember, because this said 4 seconds, that's why the information went here on the 4. I know that gravity pulls down negative 10. So this will be negative 20, negative 30. And if I go backwards, it's going to be 0, 10, 20, 30 when you go backwards. So, just like the chart we made, remember the A is negative 10. A is gravity. A is negative 10. So just like when we made all of our acceleration charts back in the day, this is how you fill it in. When you go backwards on the chart, you do the opposite sign. When you go forwards on the chart, you do the regular sign. Okay, we filled in our chart. Let's match it up. Okay, when the Vy, let me highlight this. Let me highlight this green. When the Vy is negative 20, the Vx is 20. It's not a good color. 5 seconds. Drag the 5 seconds to the corresponding vectors. Drag it. Just drag this and drop it in here. That's all you have to do. Those vectors that match, I'll get a better color. That's a terrible color. I'll highlight yellow. I don't know why I was highlighting green. Get your life, Bazzuto. Okay. Here we have a Vy of 0 and a Vx of 20. Vy, oh. Okay, here they are. Vy of 0, Vx of 20. Oh, at 3 seconds. 3 seconds isn't even an option. We're not going to use it. All right, that's fine. Oh, Vx is 20. Vy is 30. Vx, oh. Ah, check this out. Look at that. 0. You're going to, because that's 0, you're going to drag this in and drop it here. Well, there's only one left. We know it's not this one because this was 3 seconds. That wasn't. So I guess you could say I use process of elimination to know that's 2. Or correctly, you could say at 2 seconds, it's got a Vx of 20 and a Vy of positive 10. No way, get out. That's all you do. It's all about those charts. You guys got this. The physics classroom is due, but you can do it. If you've missed the notes the last few days, this really has gone over everything that we need to do. The physics classroom didn't ask about how to solve for speed, but remember, we went over that here as well. You got this. Nice. Don't forget to like and subscribe.